Good morning, everyone. My name is Muhammad Haziq bin Abdullah, and today I will be presenting on the topic of electricity and magnetism as part of PHY568. This presentation will cover fundamental concepts such as the electromagnetic model, vector analysis, static electric and magnetic field, and Maxwell's equation. This topic plays a crucial role in understanding electrics and magnetic phenomena that shape many aspects of our daily life. In this presentation, I will be covering five main topics. First, we will explore the electromagnetic model, which introduces the fundamental of natures of electromagnetic wave and their application. Then, we will move on to vector analysis, a mathematical tool that is essential for describing electric and magnetic field. After that, we will discuss static electric field, including key principles such as Coulomb laws and Gauss law. The next chapter focuses on static magnetic fields, where we will examine laws governing magnetism, such as Biot-Savart laws and Ampere's sequential laws. Finally, we will conclude the time-varying fields and Maxwell's equation, which describes how electric and magnetic fields interact dynamically. Now we will go to the chapter 1, which is the electromagnetic model. The electromagnetic model describes how electric and magnetic field interact and propagate as wave. This wave, known as electromagnetic wave, travel through space at the speed of light and make up what is called the electromagnetic spectrum. This spectrum consists of various types of wave, including radio wave, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each type of wave has its own unique properties and application. For example, radio waves are widely used in communication systems such as radio, television, and Wi-Fi, while X-rays plays a crucial role in the medical imaging. In astronomy, science utilizes different parts of spectrum to observe distant galaxies, and in our daily life, technologies such as microwave and infrared sensors rely on electromagnetic wave to function. The study of electromagnetic model helps us to understand how these waves behave and how we can harness them for various applications. Now we will go to the chapter 2, which is vector analysis. In electromagnetism, vector analysis is an essential mathematical tool that helps us describe physical quantities such as force and fields. Unlike scalar quantities, which is only have magnitude, vectors possess both magnitude and direction. This distinction of important when analyzing electric and magnetic field, as they are vector field. The position vector helps locate a point in space relative to an origin, which operative such as vector addition and subtraction allow us to combine different force or field. Multiplication of vector can be done through the dot product, which is a result in a scalar, or the cross product, which result in another vector. Different coordinate systems, including Cartesian, cylindrical, and spherical systems, are used to analyze vector quantities in different contexts. Mastering vector analysis is crucial for solving problems in electricity and magnetism, as it provides a structured ways to represent and manipulate these phenomena physical. These are the ways how to conduct converting a coordinate system from Cartesian to cylindrical or cylindrical to spherical. The del operator is a vector of differential operator used to commute gradient, divergence, curl, and Laplacian. The gradient of a scalar field represents the direction and rate of the steepest increase, commonly used in physics to describe temperature or pressure change. The divergence of a vector field measures how much the field spread out from a point, while the curl describes the rotation or circulation of a field. Lastly, the Laplacian is a second-order operator that measures how a function deviates from its average values, commonly applied in heat diffusion and wave equation. Now we will go to the chapter 3, which is static electric field. A static electric field is created by stationary electric charge and does not change with time. One of the most fundamental principles of electrostatic is Coulomb law. which state the force between the two charges is directly proportional to the product of their magnitude and inversely proportional to the square of the distance between them. This law helps us understand how charged objects interact. The electric field is a vector field that represents the force per unit charge uh, at any given point in space. Gauss's law provides another important perspective by stating the total of electric flux through a closed surface is proportional to the charge enclosed within that surface. Additionally, the concept of current density describes how electric current is distributed across a given area. Maxwell's first and second equations helps formalize these ideas, providing a comprehensive mathematical framework for the understanding static electric field. Those of the equation we are adding at the at below of our topic. Now we go to the chapter 4, which is static magnetic field. Unlike electric fields, which are generated by stationary charges, magnetic field arise due to moving electric charge, such as electric current flowing through a wire. One of the fundamental laws used to describe magnetic field is Biot-Savart's law, which allows us to calculate the magnetic field produced by a current-carrying conductor. Another important principle is Ampere's sequential law, which states that integral of the magnetic field around a closed loop is proportional to the current passing through the loops. Additionally, Gauss's law for magnetism states that the total magnetic flux through any closed surface is always zero, implying that magnetic monopoles do not exist. This principle forms the basis to understanding static magnetic field, which plays a critical roles in the operational of electric devices such as motors, transformers, and generators. Lastly, we're going through the chapter 5, which is time varying fields and Maxwell's equation. In time varying fields and Maxwell's equation, when the electric and magnetic fields change over time, they generate additional effects that lead to a new phenomenon. One example is a stationary loop placed in a time varying magnetic field, which induces an electromagnetic force according to Faraday's laws. Similarly, when a conductor moves through a static magnetic field, an induced current is produced to the electromagnetic induction. A more complex scenario occurs when a loop moves within a time-varying field, combining both motion and field variation. These effects are best described by Maxwell's equation, which summarizes the fundamental principle of electromagnetism. Maxwell's equations do not explain how electric and magnetic fields interact, but also predict the existence of electromagnetic waves, forming the foundation for modern electric and communication technologies. Before we end our presentation, in conclusion, electricity and magnetism are deeply interconnected areas of physics that govern many natural and technological processes, from the fundamental principle of electromagnetic wave and vector analysis to the behavior of electric and magnetic fields. These concepts are crucial in various engineering and scientific applications. Understanding Maxwell equations allow us to predict and manipulate electromagnetic interaction, leading to innovation in communication, medical technologies, and energy generation. Thank you for your time, and I will happy to end our presentation. Thank you.